In this video, we're going to look at some improper integral examples, all dealing with infinite bounds. So what you see here, of course, is we're finding the area from 1 to infinity, so it is an infinite bounded improper integral. I would start by rewriting this with a negative exponent. So, you know, we have 1/5 x to the -4th. Now, the next thing I'm going to do is write this in the proper notation using a limit. Okay, so I'm going to write the limit as b approaches infinity, going from 1 to b of 1/5 x to the -4th dx, like that. Now, I just want to pause for a second. Most of the time on the multiple choice or something, you probably will not do that step. You won't even think about it. You'll just integrate and think, well, it's going to infinity, so what's going to happen? However, if this appeared on the free response, they do expect you to write it, your integral, with the correct notation. And the correct notation means you see it as a limit. So I would not skip that, at least in homework. Get in the habit of doing that and recognizing that it is a limit. We're not finding the area, we're finding the limit of the area, and use the correct notation. All right, so we kind of ignore now for a minute the limit statement. I'll just put it down here, limit as b approaches infinity. The antiderivative, well, we raise the power, so it's x to the -3rd. We divide by the new power, so we have -1/15. We evaluate at b and 1. Well, the x to the -3rd, of course, I think it's easiest if we write it back now with a positive exponent. So I'm going to write -1/15. We're going to put the x cubed in the denominator, so it's like that. B and 1. So now when I plug b in, I get -1/15b cubed. I plug in 1, I get just -1/15. And I am taking the limit as b approaches infinity. Well, as b gets larger and larger, the denominator of this fraction gets larger and larger, and 1 over something getting very big approaches 0. So I end up with 0 minus -1/15, which is just positive 1/15. And this is the limit of our area. So don't forget your notation, but the big thing about improper integrals, it really is not a different process. You have to evaluate the limit at the end, but you're still finding the antiderivative. You're still plugging in the bounds, so don't let that throw you. In this next example, you're going to have a minor substitution here. I'm going to just kind of write this right underneath that, you know, u is equal to 3 plus x, so du is just dx. Now, I'm going to go at this and actually rewrite the whole thing. I'm going to do new bounds. Okay, so I'm going to have 1 over u cubed du. And remember, to get the new bounds, we simply take our old bound and plug it in, because it was in terms of x. Well, 3 plus infinity is still infinity. Okay. The bottom bound, in terms of x, it was 2. 3 plus 2 is 5, so our new bound is 5. Well, let me now do this with a limit statement. Limit as b approaches infinity, going from 5 to b. I'll rewrite with a negative exponent. Okay, so I raise the power, it becomes u to the -2nd. Divide by the new power, so -1/2. We're evaluating at b and at 5. We still have that limit out front. I've kind of run out of room, but let me just write limit as b approaches infinity, like that. Well, you know, I would like to, of course, write this with a positive exponent. It kind of makes it easier, I think, if I write 2u squared. So I get -1 over 2b squared minus negative 1 over 2 times 5 squared, so 50. Again, we're taking a limit as b approaches infinity, so as the denominator gets larger and larger, this fraction gets closer and closer to 0. 0 minus negative 1/50 is 1/50. That is the limit of our area. If you wanted to go back and at this point rewrite it with 3 plus x, then remember you would go back to your bounds in terms of x. So if you wrote it as 2 times 3 plus x squared in the denominator, your bounds would be infinity, or b and 2. Okay? All right, one more example. We're going from negative 1 to infinity of e to the negative 5x. So let me rewrite this. Or let me first just think about our substitution. Put it right down here. That u would be negative 5x. So du would be negative 5 dx. So we divide both sides by by negative 5. Give myself a little room to put that negative. Okay? So, let me rewrite. I'm going to have a negative 1/5 out front. I have an integral. Me e to the u du. Now, here's what's kind of interesting. If I plug in infinity to hit this, negative 5 times infinity, well, this is now negative infinity. If I plug in negative 1, negative 5 times negative 1 is 5. Okay. Well, I should write this with a limit statement. Still got the negative 1/5, but now it's going to go from b, from 5 to, and I could make it negative infinity and just have that. Well, the antiderivative of e to the u is e to the u, so limit. So I plug in b, plug in 5, take the limit as b approaches infinity, negative infinity, excuse me. Well, if I plug in negative infinity here, let's do that. E to the infinity, of course, is infinity, but e to the negative infinity, this is like 1 over e to the infinity. Well, that's getting closer and closer to 0. So we end up with just 1/5 e to the 5th. So sometimes the limits are a little tricky. You need to think about them a little bit. But most of the time they're not too bad. I guess one other thing I would point out, because the bounds here are a little bit odd, that we're going from 5 to negative infinity. We don't usually like that. Why that happened was because our u was negative. And usually we say, well, if the bounds are wrong, don't we put them in the right direction and change the sign? We certainly could. If we did that, if we went from negative infinity to 5, then we'd make this a positive 1/5, and we'd end up with the positive 1/5 e to the u, evaluated at 5 and b. We're going to come out with the same thing. Okay, which of course makes sense, that if we're going to do the right adjustments to our integral, we're going to get the same thing, but it really wouldn't matter.